Thousands of highly capable open-source AI models are now available. The promise is a future of private, unrestricted intelligence arriving right at your desk. But the reality is often different. A user downloads a top-ranked model onto a high-end rig, only to have the system freeze or produce text at a painful 1 word per minute. It leads to a clear contradiction. A computer that can render complex 3D worlds with ease often chokes when asked to run a simple text generator. These failures happen because raw hardware power is only half the equation. If the model's internal architecture is misunderstood, even a high-end system will fail to run it. Large language models do not follow standard system requirements. Whether or not a model will function depends on its physical sizing. Navigating that size requires managing several variables, accounting for billions of parameters, vastly different architectural structures, dictating how the model occupies space. When the model's footprint exceeds the specific hardware constraints of the machine, the system cannot sustain the logic, and the generation fails. Running AI locally requires a physical alignment between the model's shape and the machine's specific constraints. To solve this bottleneck, we have to look at the 2 memory gates inside a computer. System RAM handles general tasks with high capacity but lower speeds, while GPU VRAM provides the hyper-fast processing required for AI. Optimal speed requires the entire model to reside within the fast VRAM ring. If too large, it spills over, forcing excess data into the slower system RAM. This memory bandwidth bottleneck collapses generation rates as the system struggles to move data between pools. VRAM capacity is the primary barrier to local AI speed, forcing developers to find ways to shrink these massive models. The most common method for shrinking a model is quantization. It is a mathematical compression technique designed to fit massive data into limited hardware space. This process reduces the mathematical precision of the model's parameters, creating a smaller, blockier version that finally fits inside VRAM. However, there is a trade-off. As the physical footprint drops, the AI's logic and reasoning capabilities drop with it. Quantization is a constant compromise between model size, generation speed, and intellectual quality. Calculating this compromise across thousands of models is a nearly impossible task for a human developer to perform manually. The terminal tool llmfit handles this automatically. It acts as a matchmaker between specific hardware and the models available today. By detecting your local system specs, it scores models across 4 dimensions: memory fit, estimated speed, quality, and context length. It also accounts for advanced architectural differences, such as the active parameter footprint used by mixture of experts models. This shifts the process from frustrating trial and error to a precise hardware calculation. Theoretical math provides a starting point, but physical hardware under thermal load often behaves differently than an estimate suggests. This makes global AI leaderboards unreliable for local use, as they cannot account for your specific cooling, power limits, or memory configurations. To address this, the llmfit share feature allows users to run actual benchmarks and anonymously contribute real speed data back to a central catalog. This approach moves the local AI ecosystem away from theoretical assumptions and toward verifiable evidence. This crowdsourcing process creates a compounding benefit. Anyone with matching hardware can now see verified speed expectations before they spend time on a massive download. Relying solely on the best model on a global leaderboard is an inefficient strategy for local development. The future of this field depends on these hardware-specific benchmarks replacing generic estimates. Ultimately, effective local AI development focuses on finding the smartest possible model that integrates perfectly with your existing hardware.